The average person looking back at the 19th century typically sees a time of high-button shoes, mud streets, and travel by horse and buggy. But with electric lighting, there was a great deal of complex technology. This was particularly true in the area of arc lighting. Arc lights were contemporaries of incandescent lights, both being developed around 1880. Arc lights were typically used outdoors as street lights or when indoors in such places as large train stations. Incandescent lights were more suitable to indoor use because their lights were less brilliant. Power distribution for arc lamp street lighting took several forms. Both direct current and alternating current systems were in use. In each of these systems, the lamps could be either series connected or parallel connected. Parallel or constant potential arc lighting systems were better for use in buildings where the lamps were not a great distance apart. Where larger distances were involved, such as street lighting, the series distribution system was very common. Notice that the parallel system requires 2 conductors to be run to each light. For a mile of lighting, 2 miles of wiring would be required. With the constant current system, however, only 1 mile of conductor would be required, and because the current was constant, additional load did not require a larger size conductor, just additional voltage. During the 19th century, the steam engine was the prime mover of choice. Steam engines used governors to keep their speed constant. Constant speed was typically required by production machinery. Steam engines, with their use of line shaft and belt drives, had an overall efficiency of less than 10%. By the beginning of the 20th century, electric motors were coming into widespread use. An electric motor had an efficiency of not less than 80%, even in the most inefficient early models. Now, since each machine typically had its own motor, constant speed was an easily obtainable feature. The equipment in these constant current systems of the 19th century would be unrecognizable to a modern engineer. Since motors increase or decrease current in an attempt to maintain constant speed, the use of motors on a constant current system offered financially unassailable challenges. Because a practical motor was not available for constant current systems, the days of these series systems as a supplier of power other than for lighting were numbered. But in the case of dedicated lighting systems where transmission distances were large, it was a different story. The cost involved allowed series lighting systems to last well into the 1950s. And now we'll have a look at how a series constant current arc lamp operated. It should be understood that the movement of the upper electrode will be shown in discrete steps in order to better depict the operation of the control system. In actual operation, the only movement noticeable, assuming that you are wearing a welder's helmet, would be the top of the upper electrode slowly moving down as it was consumed in the arc. Shown here are the components of a DC constant current arc lamp. Constant current means that the current flow does not change as the load increases. It is the voltage that changes. The switch is shown closed. This shorts out the lamp so that it is not in operation. Opening the switch places the lamp in operation in the series distribution circuit and the carbon electrodes separate. Current flow will be shown from positive to negative, as was the convention in the 19th century. The arc voltage is controlled by the arc gap between the positive and negative electrodes. The operation is as follows. The switch is shown in the open position, placing the lamp in operation. Current flows through solenoid S1 and then through the top electrode, into the arc, and through the bottom electrode and back to the line. A solenoid, of which there are two, one inside the other, is simply an electrical conductor coiled around a metal core. In a more or less standard convention, an X represents current flowing away from the viewer and a dot represents current flowing towards the viewer. This current flowing in S1 produces an upward acting magnetic field represented by the arrow S that acts in opposition to gravity, producing an upward force on the top of the electrode by means of the clutch carrier and the clutch. The top carbon electrode will move upward and open the arc gap. The magnetic force S1, produced by the current flowing through the arc and into the solenoid S1, is adjusted so that it just balances the weight G of the upper electrode, the clutch, and the clutch carrier at a point where the arc is the proper length. Carbon was the common electrode material. During normal operation, the carbon is vaporized in the intense heat of the arc. As a result, the electrodes are shortened and the arc lengthened. The upper electrode is consumed approximately twice as fast as the lower electrode. Now we'll look at the part that S2 plays in the story. On the right is a simplified version of the arc lamp schematic shown on the left. Only the electrical components are shown. Let's have a closer look. The current flowing in the arc lamp's power circuit, IS1, produces a voltage drop across the resistance of the arc VARC. All conductors, even the ionized gas in an arc, have resistance. The length of the arc gap results in an increasing voltage drop across the arc, causes a current to flow through S2. The S2 coil is wound in such a direction as to oppose and balance the force from S1. Because S2 is wired across the arc gap, its weakening effect on S1 is in proportion to the length of the arc. The longer the arc gap, the greater the voltage across it. As a result, more magnetizing current flows in S2. The magnetic field from S2 opposes that of S1, and the overall field is weakened, allowing gravity to begin to move the upper electrode down, closing the arc gap and reducing the weakening effect of S2. The original balance between the two magnetic fields is re-established, and the gap is brought back to the proper length. This early example of electric feedback control used magnetic levitation to control the arc. Now that we've looked at the control of the arc gap, we'll look at the problem of feeding the top electrode down to replenish what has been eroded by the arc. We'll look at several example intervals during the operation of the lamp. At A, the arc is burning and the gap is in the control range. At B, the gap has widened due to consumption of the carbon. At this point, the arc is not capable of efficiently producing light. The voltage across the arc gap has increased and, as described previously, causes the upper electrode to move down to close the gap at C. The top of the upper electrode at C has moved down as well because it has been shortened as a result of the consumption of its carbon in the arc. The process begins again at D. More carbon is consumed and the arc has lengthened to the point where control action is again initiated. At E, the proper arc gap length has again been restored, and the process repeats, but now the length of control of the solenoids S1 and S2, no more than a few inches, has been reached, and the clutch comes into play. In our example, the clutch takes the form of a disc with an internal diameter slightly larger than the outer diameter of the top electrode. Notice that in our description up to this point, the clutch has been tilted, grabbing the electrode. This allowed the clutch carrier to adjust the arc under the control of S1 and S2. A stop is provided near the point where the upper carbon has shortened to such an extent that it needs to be fed downward. When the stop is contacted, the electrode drops down, shortening the arc. S1 and S2 react to the change in voltage across the arc, pulling up the clutch carrier and causing the clutch to tip and grab the electrode, at which point the control of the arc is reestablished. What you've seen here is a brief intro to arc lamp operation. There's a great deal more to the story. For anyone wishing to look into the topic, I provided this list of references. The International Textbook Company, later known as InText and then International Correspondence Schools, is a good place to start. At the turn of the 20th century and into the 1960s, they provided a very good series of courses with textbooks that had excellent descriptions of apparatus accompanied with well-executed line drawings of equipment.